Welcome to this module. In this module, like I discussed in the last module, we will be discussing the application of an op-amp. Application of an op-amp is a peak detector. Now guys, you see, slowly and gradually I am trying to show you several applications. We have started just from characteristics of op-amp, just input offset voltage, input bias current, very simple, right, and then we move to little bit complex circuits, and here you see that we have reached to the circuits where you can really use this circuit in some actual electronic module. For example, if you talk about peak detector, you will see in one of the ADCs you use this comparator and you are comparing the voltages, which is your flash ADC. So now what we are looking at the electronic circuits that we can design using op-amp, and those circuits you can further use it in more complex circuits. So this little bit we are increasing the complexity of the application. Here we will look at the op-amp, how it can be used as a peak detector. Okay. So let us see on the screen how we can design this. So when you talk about op-amp as a peak detector, the first thing that you have to see is the function of the peak detector. So function of the peak detector is nothing but to find the peak value of the input, right. So what is the peak value of the input? If you want to know, you can use the circuit which is your peak detector, alright. That means if I have an input signal, right, like this, what is my peak of the input? So is this the peak or is this the peak? If this is the peak or is this is the peak, right, which one is the peak of my input signal? If I want to understand, right, if I want to understand, then I can use the circuit which is the peak detector. The circuit shown in the figure, which is here, right, it follows the voltage peaks of a signal and stores the highest value, it stores the highest value on the capacitor. That means we have a capacitor, here. Now we apply input signal here, okay, we apply input signal here, then based on the input signal, based on this input signal, my if my anode is positive compared to cathode, my anode is positive compared to cathode, this will act as a voltage follower, this will become a voltage follower, or it will become a buffer, right, buffer voltage follower, it will become a buffer or it will become a voltage follower, right. So when it is a voltage follower or a buffer, what will happen? That my capacitor will start charging, and here at the output we will be able to see a signal, right. So when I have input voltage which is this, right, instead of just sine wave, if I have input voltage which is varying in nature, like you see, this is my input voltage, I will draw it here, or I just draw the same signal. The red point that I have drawn is my input signal. Now which is the peak I want to know. So initially when it reaches to this particular value, right, my capacitor will start charging and it will store this value until a peak which is higher than the earlier peak will appear, my capacitor will remain saturated or it will have same voltage. As soon as I see the signal at the input higher than the previous signal, higher than this particular signal, right, you see the capacitor again starts charging, it will again keep on holding the same signal, until another peak appears which is higher than the previous peak, which is higher than this peak. So you can see this peak is higher than this peak, right. If I say P1 peak 1, P2 peak 2, P3 peak 3, then P1 is less than P2 is less than P3. That is why if I just draw the capacitor signal, then what I look at it, I look at a signal like P1, okay, then it is holding it, then as soon as peak 2 appears, peak 2 holding it, peak 3 holding it. So if I just see this graph, right, then I can see that my signal that appeared at the input, the peak value is this one, right. Super easy to understand and super easy circuit to implement, right. What you require? You just require one diode, you require just one single diode and a capacitor, and of course your operational amplifier, alright. operation amplifier. So, let us see. Okay. The circuit shown in figure follows the voltage peaks of a signal and stores the highest value on a capacitor. That is what we discussed. When a higher peak signal comes along, the capacitor will be charged to the new peak input voltage or new peak input value, right. This is what you see from here to here. Thus, the capacitor stores the peak value by charging the capacitor until it is discharged, right. So, it will hold the value, this capacitor can hold the value until you discharge it, If Vi is greater sorry if Vi is greater than Vc, if Vi, this signal is greater than the voltage across capacitor, diode D is in forward bias, agreed, because you see then this will be at higher potential compared to here, that is why anode and cathode. So, diodes will be in forward bias, but what will happen if Vi is less than Vc, then diode would be in reverse bias, correct. So, now first let us see the first condition, Vi is greater than Vc. When Vi is greater than Vc, my diode is in forward bias. So, forward bias circuit becomes a voltage follower, because when forward bias is there, it will be like this. So, circuit becomes my voltage follower, hence the output voltage Vo follows Vi until it exceeds the Vc voltage. Now, what if Vi is less than Vc? Vi is less than Vc. In this case, my diode will be reverse bias, right, because my input signal, that is the signal or voltage at anode, is less than the voltage at cathode. Voltage at anode is less than the voltage at cathode. That means, my diode is reverse bias or diode becomes reverse bias, and hence the capacitor will be disconnected, right, as if the circuit is open. So, if I draw that when the diode is not there, then what will happen? I have just op amp, right, diode is not there. So, I have no capacitor here. So, my circuit is disconnected, right, because diode cannot operate, because it is in reverse bias, circuit is disconnected or diode is disconnected from the circuit, and hence my capacitor holds the peak input value until the input signal again attains a value greater than Vc, right. That means, initially if Vi is greater than Vc, capacitor will start charging. When Vi is less than Vc, this diode is disconnected. So, capacitor will hold this value. Again, when your input signal is greater than your Vc, then again your diode will conduct and your capacitor will again have a different charge value or different voltage across the capacitor. The application of this peak detector, understand, now we are also showing the application, right. I told you that slowly and gradually we are moving to circuits, or we are moving to the point that now you guys can design the circuit and also understand what exactly the application of these circuits are. So, the application of peak detector include in test and measurement instrumentation, as well as in amplitude modulation communications. You may have studied in electronic communication course in your undergrad what are amplitude modulations, what are frequency modulations, right, and what kind of circuits are there for amplitude modulation and frequency modulation. So, if you talk about amplitude modulation communications, then you will see a similar circuit what we have shown today, which is your peak detector. So, now it is very easy, right, very easy to design this peak detector, it is very easy to understand the peak detector, and let us try to implement this peak detector on the breadboard, and then for implementing this peak detector, we will take the circuit which is shown here, and we will also implement on the multisim, so that you guys understand how it is different when we are using breadboard and how it is different when we are using multisim. So, to study the working of peak detector, that is our aim, right. First is we can connect the circuit as shown in figure 4. It is exactly similar circuit. This is nothing but if you connect it, then the you can connect the capacitor directly to the, you can short the capacitor to the ground, means the capacitor will be out if you connect here, right. So, that is just a switch. Apply a sine wave input 5 volts, 5 kilohertz voltage from generator at V1. I think 5 kilohertz we have to apply at the input signal, and we can vary the voltage in a step of 1 volts. Observe the output across the capacitor C and comment on the output voltage. So, for designing, for showing you the experiment, this particular experiment on breadboard, let us welcome Anil Vishnu, and he will show us how we can implement the circuit on the breadboard, and we will be able to see the circuit. So, if you now can see the breadboard, yeah, you can open the probe. Let me show them the breadboard. So, if you see the breadboard here, right, in my hand, yeah. So, what we are able to see? We are able to see a capacitor, right, if you can focus, yes. So, it is a capacitor, then we have a diode, we have operation amplifier, right, we have an operation amplifier, and my diode is connected, so this anode, the cathode is connected to the capacitor, alright. So, this capacitor is connected to the cathode, and then I had to measure the output from here, I had to observe the output from here, right. I had to apply the bias voltage across the operational amplifier, alright. So, when I do all these things, when I apply bias voltage across operational amplifier, apply the input at the op amp, I will be able to see the output from the operational amplifier. This is what we will do today, and for that we have to attach the 5 kilohertz. When we say, that means we have to use the function generator, So, we have our DC power supply, then we have function generator, and we have oscilloscope. 3 things we have: DC power supply, function generator, and oscilloscope. The first is we are connecting the bias voltage. So, plus 15, minus 15, plus 15 and minus 15 across the op amp, we can see this. Now, we have to apply the input voltage, 5 kilohertz 1 volt peak to peak to the 5 kilohertz 1 volt peak to peak to the input of the operational amplifier or input of the peak detector. So, now you can see right that now we have connected the probe, first probe 1, and then we are connecting the output of the peak detector, to the oscilloscope. So, you can see the signal, input signal, and then we can also see the corresponding output signal, right. Okay. Now, this is at 1 volt, alright. We are applying 1 volt and frequency is 5 kilohertz, Yeah. So, now we are slowly increasing the voltage. You can see now 2.6, you can see it is following the peak, maximum peak, right. It is following the maximum peak of the voltage. You can see now it is connected. Okay. So, now you are again he is decreasing and you can see it is following the input signal, increasing again it is following the input signal, right. So, you can see it is working excellently and you can clearly see the follow of the peak detection, the highest peak that you can find in the input signal, it is following it. So, this is how you can increase the voltage, right, and in the input signal or decrease the voltage in the input signal and try to see how you can design the peak detector and what is the output of the peak detector when you are changing the input signal, alright. So, yeah, that is enough. So, now let us see the same circuit, in the multi-sim and how we can design this, how we can design the similar circuit that we have designed on the breadboard, right, on the breadboard or using the multi-sim, So, for designing the same circuit on the multi-sim, we will do the same thing and we will ask Sitaram to join us. So, Sitaram is with us and now if you see the screen, what we are doing? We are creating a new file, we are saying we are creating a new file and we are saving the old file. So, that if you want to run the simulator again we can use the same circuit. So, we have created a new file, a blank file, and then here we will again do the same thing, we will drag the operational amplifier or a comparator. So, operation amplifier because it is a voltage follower that we can use it, voltage follower, and then we are connecting the output of the op amp to the diode. We are exactly trying to make the same circuit which you can see on the left side of your screen, alright. We are trying to design the circuit which you can see on the left side of your screen using the multi-sim. So, when whatever he is trying to implement, look carefully, right, and try to do at home. This is a free software, so you can try and test your circuits. This is ground. You connect the signal, right, connect the signal and then connect the inverting to the output, right. Now, do not forget guys to ground the power supply or the output, otherwise you will not be able to see the output voltage whatever we are trying to observe. Now, you are selecting a switch, and he has to connect the switch across the capacitor. As you can see, he is connecting it, you have to just drag it and drop it. Now, we are looking at the voltage at the input and we are looking at the voltage at the output or across the capacitor, and we are looking at the output signal. So, when we press run simulation, you will be able to see that right now my voltage is about 1 volt and my output voltage is also close to 1 volt. If I change my voltage, you see my output is following, the highest voltage that is available in the input signal, right. You see it is only showing the highest voltage or the peak voltage in the input signal, So, that is the beauty of simulation, that you can play with the voltage at the input and immediately you can see the change in the output. You really do not require the DC source or the function generator or the oscilloscope to get these results. But when you actually fabricate or design the circuit and if you use the breadboard, you will find lot of actual or practical difficulties, and that is why it is always good to not only do the simulations, but also to try your circuits on the breadboard. Now, you can see here when he is changing the voltage, you can clearly see that the output is following the peak of the input voltage. Output is following the peak of, or it is detecting the peak of the input voltage, right. If you decrease the voltage, it is following, if you increase the voltage, it will just detect the peak, it will detect the peak. So, excellent way of quickly looking at the circuit working or working of the circuit, and this is how you can implement the peak detector. This is how you can implement the peak detector. So, the point is that you can understand the theory which we have understood now, how peak detector works, then we can make the circuit which we have made on the breadboard, and finally you are able to look at the simulation, right, using the multisim. So, having said that, now we have to still see, we are not done, we have to see further applications of the operational amplifier, and in the next class what I will try to show you is the another application of operational amplifier, that is your clamper. What is clamper? You clamp, right, you clamp. So, we will see how you can design a clamper. It is a CLAMPER clamper, and we will also perform the simulation on the clamper and on the breadboard as well, we will see on the breadboard as well. So, or rather let us not do on the breadboard, because we have now already know that how we can implement the circuits on breadboard, and I do not want to show you the same circuits on the breadboard, or because now I am sure that you are able to perform the experiments by yourself. The idea of you of the idea of me showing the experiments to you was that you are able to now demonstrate whatever things you are learning in the theory in terms of experiments using the breadboard, and I feel that to this extent whatever we have done it is good enough for you to as a getting a basic understanding of how to use the equipment, of how to use the breadboard, of how to implement the circuits. You take care. Bye.